In this video, we're going to start talking about how we can use different applications of the quadratic functions, and we're still going to focus on using GeoGebra as a technology tool we have for graphing quadratic functions. And in the first example, feel free to pause the video to read the paragraph on your own, otherwise I'll kind of talk about the background setting. And the background is about this experiment at OMSI. You can check out the video for exactly what's happening. Basically, they have a dry ice explosion experiment that's been demonstrated in the video. And to demonstrate this explosion with dry ice, they are using a bunch of ping pong balls. And let's say if one of the ping pong balls is launched into the air in such a way that its height, measured in feet, t seconds after being launched can be modeled by this quadratic function over here. Then we want to kind of explore what exactly is a ping pong ball doing through its whole projectile movement in this process. And to do so, the first thing we need to do would be to graph this function in GeoGebra. And I'm going to first type in this function over here. Let's call it h of t because it's talking about the height. And you can see on the bottom screen that's where the input bar is, and we have h of t is equal to negative 16t squared plus 40t, I believe, then plus 2. And that's the scenario we have over here. You can already see that we have this image of the function over here. I'm going to move it up a little bit just so that we can see the entire function graph over here. Feel free to adjust the window to zoom in and out as you need to, just so that you can see all the key features of this parabola in this case. And to answer our questions, the first thing we want to do is to go ahead and determine the vertex and the axis of symmetry, and more importantly, for any application problems, we want to think about what does these key features tell us about this function in the scenario, and what does it mean in our given situation. So first, if we want to find the vertex, we want to go ahead and use the tools we have over here. First thing, if we need a vertex, we know the vertex is a point, so I'm going to use a pull-down menu under point, and we can use the extremum to show us the highest point, the lowest point for our graph. And if we click on this, we can just go ahead and select the parabola. What this shows is going to be the highest point we have, which will be our vertex. And if you look on the side, we can find out the coordinates for the vertex, which is 1.25, 27. And I'm going to go ahead and record that into the worksheet. So we know the vertex over here is 1.25, 27 over here. And then we want to also find the axis of symmetry. We know that the axis of symmetry is a vertical line that's going through the vertex. So if we just look at the vertex, we should be able to get the axis of symmetry from this information. If it's a vertical line, we know that it's going to have the equation in the form of x equals some value. And we already know the x coordinate for the vertex is 1.25, so we can say it's x equals 1.25. And if you want, you can also check your answer through GeoGebra as well if you just type in the line. In this case, we actually have t as the input. I should have corrected myself for that. And if we have t equals 1.25 as the line in this process, we can actually go ahead and graph it. And just through this process, I noticed that for GeoGebra, it'll only recognize the independent variable over here as x equals 1.25. So instead of typing t equals 1.25, we should do x is equal to 1.25. Then we can actually see this is indeed the vertical line that goes through the vertex, and this is going to be our axis of symmetry. But meanwhile, we can rewrite this axis of symmetry in our worksheet to be t equals 1.25 because we do have that flexibility in terms of what variable we want to use as the independent variable. And now we want to think about what does the vertex and the axis of symmetry tell us in the context of the scenario. So the first thing about the vertex, we have 1.25 comma 27. And if we look at what each coordinate represents, we have the independent variable being t, which is a number of seconds after the ping pong ball was being launched, and 27 was the height being measured in feet. So to interpret it, we can say that after 1.25 seconds of the launch, the height of the ping pong ball is going to be 27 feet over here. And then to interpret the axis of symmetry, we can look back to GeoGebra and see this is where the graph shows a symmetrical feature in our parabola. And we can say that the axis of symmetry is essentially the moment when the ball starts dropping, when the height is starting to decrease over here. So from the axis of symmetry, we can say after 1.25 seconds, the ping pong ball starts dropping. In this process. And now if we want to determine what we have for the next part, the y-intercept and its mirror point, we can again use the technology we have, but we also know that if we want to find the y-intercept, we can still use a tool of plugging 0 into the independent variable t and find the y-intercept. So we can kind of check our answer algebraically and then use GeoGebra to kind of compare what we have done algebraically versus using technology. So if we want to find the y-intercept, that tells me the independent variable is 0, so t equals 0. And when I'm looking for this, that really tells me I'm looking for h of 0. That's a starting point we have. And as we plug 0, we get negative 16 times 0 squared plus 40t, so 40 times 0, then plus 2. And altogether, you should be able to see this is equal to 2 feet over here, because we are looking for the function value, and the function value has a unit being feet. And we can check through GeoGebra to see whether we indeed get the height is 2 feet when t equals 0, and write out the y-intercept from here. So going into here, if I want to find the y-intercept, you can see we need to go down a little bit. It's right over here. That's going to be the y-intercept. And to find the y-intercept again, it's going to be a point. And in this case, for the point, we're actually going to find where the curve intersect with the y-axis. And therefore, I'm going to go under the point again where I found the vertex. So under the point, there's the intersect, and we can select the curve and select the y-axis. And we can see they intersect at the point B, which is indeed 0, 2. That's what we found through the algebraic method as well. So we can say the y-intercept is 0, 2. And then we want to find the mirror point of the y-intercept as required by the problem. So if I want to find the mirror point over here, we can use this icon on the top, reflect about line. It's the third one from the right, and the first option should be reflect about line over here. And if you click on it, we can click on the point B, which is a y-intercept, and click on the axis of symmetry, and it'll give us a point B prime. That's going to be the mirror point, which is on 2.5, comma 2. And as we put it here, we can say the mirror point is 2.5 comma 2 over here. And with this, we want to talk about what do these points mean over here. In this case, when we look at the 2 points, the y-coordinate is 2 for both cases, meaning what it represents, the height is always going to be 2. And with this information, we can say that the height is the height of the ping pong ball is 2 feet, essentially at these two moments. So the first one is 0 seconds and the second one is 2.5 seconds after launch. So basically, initially the ping pong ball was starting off at 2 feet. It didn't start at the ground, and then it'll get back to this height after 2.5 seconds. And now we want to think about, in part D, what are the x-intercepts and what do they mean in this case? So x-intercepts is something that the technology is going to be really helpful for, because if we look at the original function, it's going to take a little bit of work in order to find where we can have the x-intercept or y is equal to 0 over here. So if we want to look at the x-intercept, we're really thinking about where h of t is equal to 0 on the graph. And looking back to this, if I want to find the intersect, I can do the same thing as what I did before using the intersect function. We can find where the function intersects with the x-axis. Remember to click when you see this hand icon. That means you're selecting the object. And there we see there are 2 points as C and D over here. And I'm going to go ahead and record both points because they are both technically the x-intercepts for our graph. So it's at 2.55 and t equals negative 0.05. So we get negative 0.55, 0, and 2.55, comma 0. These are the x-intercepts, or really our t-intercepts over here. With this information, we can think about what are these points? What does it tell us about the graph? And if you think about this parabola, what it represents is really the trace of what this ping pong ball was doing. It started at the height 2 at 0 seconds and moved up and then eventually dropped to height 0. And when we look at the 2 points, you'll notice if we look at the point C, t is equal to negative 0.05, meaning it's a negative time for our interpretation. So when we interpret this point, it's actually meaningless because we can't really have a negative time for our scenario. So based on this, we can say that this point with a negative coordinate is meaningless in the context, because t is less than 0. And we can't really interpret a negative time. Versus for 2.55 comma 0, this is where we can talk about, this is saying 2.55 seconds after launch. The height of the ball is going to be 0 feet, or we can say the ping pong ball hit the ground. And that's how we can interpret it. And then for part E, if we want to find the height of the ping pong ball 2 seconds into its flight, when we are given this type of scenario, we want to first translate it into the notation that we're using for symbolic representation. So if it's 2 seconds into its flight, because it's a time, that tells me t equals 2 over here. So for t equals 2, we can actually get the point over here. we can find h of 2 equals what value, and that would give us the height of the ping pong ball over here. And just to make our graph a little bit easier to read, I'm going to go ahead and hide a lot of the points that we already looked at and just leave the function graph over here. That way we have less distraction. And if t equals 2, that means I'm tracing along the graph until t equals 2. And we said if we want to find this particular point, we can type in the input x equals 2 over here. And once we have this one, we can find the point over here in terms of where they intersect. And as you click on the intersection, you will see the point being 2, 18 is where it hits. So we can say when t equals 2, the height is equal to 18 feet. And we still use intersect function to find where this vertical line of t equals 2 seconds and this parabola intersect with each other. So we can say that h of t equals 18. So we can say the height is 18 feet 2 seconds after the launch or into its flight. Lastly, if we want to find when the ping pong ball will be 10 feet off the ground over here, that's when we know the height. So if we know the height already, that tells me h of t is equal to 10, or you can think about the y value on our graph is equal to 10. Going back to GeoGebra, again going to kind of hide the other distracting points. So if I want y equal to 10 feet in this scenario, that's what we need to graph. And then if I want to find the intersect, I can again select the 2 points that they intersect at over here. I have the point G and H over here. And with the points I get on the left, we have 0.22 and 2.28 being the first coordinate, or t equals these values. I accidentally hit the first intersection twice. So you'll be able to see that these are the two intersections between the parabola and our line of y equals 10. So I'm going to record these 2 points on the worksheet. Let me just quick check. 2.28 is what we have. And this is what we get for the 2 points. With this information, we can answer the question and say if it's 0.22 seconds and 2.28 seconds into the flight, the ping pong ball will hit the height being 10 feet. And we can see exactly from the graph, it'll hit it twice because it hits it once going up and once coming back down to the ground over here. So we can say the ball hits 10 feet, 0.22 seconds, and 2.28 seconds into the flight.